All right, this is a kind of a long discussion on complex numbers. A while back, you probably learned that a complex number has the form of a plus bi, and in this case, we're just going to let z represent it. What we're going to eventually do is bring complex numbers into the modern world. Right now, you can just mess around with, a plus bi and a minus bi. Remember, these things are called conjugates. To represent that with the letter z, we just put a little bar over it. So the z is a complex number, z bar is its complement. And a few things about complements while we're here. Z plus z bar, if you add them together, the bi parts are going to go away, so you're just left with 2a. And if you do z times z bar, the multiplication of conjugates, this just becomes a squared plus b squared. And the reason behind that is you have to remember one fact about imaginary numbers, well, two actually. I by itself is equal to the square root of -1. It's just a representation of square root of -1. And therefore I squared is equal to -1. So anytime you see an I squared, you're going to get a -1 out of it. All right, so this is old-fashioned complex numbers, and if you want, we can practice one. If you have 2 minus 3i, and you want to multiply by its conjugate, just to play around, this is 2 plus 3i. And then we're going to FOIL, so 2 times 2 is 4, 2 times positive 3i is 6i, negative 3i times 2 is negative 6i, and negative 3 times positive 3 is a negative 9, but then you have the I times I, which is I squared. So the middle two terms are going to cancel out, which is nice. The I squared is going to become -1, and you're going to have -9 times -1, so you get 4 plus 9. And thus we have that formula a squared plus b squared. And it works out for conjugates. So all the old stuff that complex numbers used to be able to do was add them, multiply them, divide them. Those are the three things you could do with them. And subtract, but that's the same thing as addition. So what I want to do is I want to be able to take powers of these things rather quickly, and I also want to be able to take square roots and cube roots. So the first step in that is to change the way we look at an imaginary complex number. So here we're going to take the normal coordinate system that you're used to, and we're going to change it just slightly. We're going to let x still remain as real numbers, regular old x-axis, but in this case we're going to let the y-axis be represented of the imaginary numbers. So if I have 6 plus 3i, in this complex coordinate plane, this becomes the coordinate 6, 3. So you'd go 6 along the real axis and then 3 along the imaginary axis. And this coordinate right here represents 6 plus 3i. It's kind of a cool thing. And we can move this anywhere we want in this coordinate plane, and each one of the points would represent a complex number. All right, if we can do that, let me switch up here. If we can do that, then we should be able to take this point, put it anywhere we want, and you'll notice I have a line attaching it here. That's going to become the radius. I'll move that right over there. And if you want to also think about it, we also have an angle from the positive x-axis to this radius, and therefore we can take this coordinate and change it into polar form. In the case of this, it would be r is equal to 9.22 and the angle is equal to 49.4. So it's kind of like polar form for complex numbers. So it's kind of a weird idea, but it comes from this idea that you can plot an imaginary number in an imaginary or a complex coordinate plane. All right, so let's see what we can do with this. Back to this program. Next page. So here I drew 7 plus 6i, and what I want to do to it is I want to see how to change it into polar form. So the first thing I'm going to do, ooh, that's way too thick. Let's do this size. Is I'm going to draw down straight down below the point. I don't know why this program doesn't like straight down. And of course, form my little triangle. Try to. There. Close enough. So what we know about this triangle is this side has a length of 7, this side has a length of 6, and we're looking for the third side. So we're going to get r squared equals 7 squared plus 6 squared, just like polar coordinates. So in this case, r squared is equal to 49 plus 36. That's 70, 85. So you're going to get r is equal to the square root of 85. All right. Then the second part that we need is this angle theta. So to find theta, theta is equal to tan inverse, just like with polar coordinates, of opposite over adjacent. So this is approximately, let's see here, second tan inverse of 6 divided by 7, 40.6 degrees. And I'm going to stay with degrees, but technically you should be writing this in radians. All right, so we know what the radius is, and we know what the degrees is. But I really don't want to change this idea that it's 7 plus 6i. So another way of looking at this is to come up with the 7, let's just call it x, and let's call this side r. We know that x is equal to r cosine theta. And we know also, if we call this y and the other side r, that y is equal to r sine theta, according to polar coordinates. So we can take this and separate it as the radius, which is the square root of 85, cosine of the angle, which is 40.6, and that would represent 7. Then we have plus the 6i, and that's going to get represented by the radius, square root of 85, times, and don't forget, in here, I almost forgot, there's that I that I always forget about. But the I is here, so I have to take care of it. So the 6 is the square root of 85 sine, but I got to throw that I in there, so I'm going to place it in this area. Sine of 40.6. Don't forget my little degree signs. There. So we can change 7 plus 6i into this really long expression. And there's really not much use of changing it over, except it's really hard to find cubes and fourth powers of 7 plus 6i, and it's really not that hard to do it to the right-hand side. So polar form of complex numbers is only usable that I can think of finding roots and powers of a complex number. All right, so here's the equation. A plus bi is equal to r cosine theta, I sine theta, where r is equal to the square root of a squared plus b squared. The modulus, I think it's called, modulus. And theta is equal to tan inverse of b over a. And this is called the argument of the polar form. All right, so let's see how to change things over. Let's say we have 3 minus 2i, and I want to change it into polar form. We've got to be a little bit cautious because tan inverse only works in the first and the fourth quadrant. 3 minus 2i is in the fourth quadrant. Let's make it negative 3 minus 2i. There, we're in the third quadrant. Tan inverse doesn't work there. So the best thing to do, even though you might not want to, is to draw a picture. So we're going to draw where 3 minus 2i will land, and then we can talk about what the tan inverse of it is. Okay, back to this. So negative 3 minus 3 minus 2i, negative 3 minus 2i, is going to be negative 3 along the real axis and then down 2 on the imaginary axis. So this would be negative 3 plus 2i. Let's just call this z so I can label this as z. Alright, so the next thing I need is some little line segments. Make my little triangle. So here's our angle. And I'm not going to bother with the triangle. I'm just going to use the formulas. So I can find the length of that green line. That's not hard. That's going to be r equals the square root of the square of these numbers added together. So negative 3 squared and negative 2 squared. So the radius of this thing, or the modulus of this polar form, is square root of 13. But when I do tan inverse to find theta, I have to be careful because we're in the third quadrant, and tan inverse does not work in the third quadrant. So let's see here. It's b over a, so this will be negative 2 over negative 3, also known as 2/3. So in the calculator, tan inverse of 2 divided by 3, it's going to give me 33.69. Well, 33.69 is this angle. The angle I want is the one that puts me into the third quadrant. So there's two ways of dealing with this. I can leave the angle alone as 33.69, but then I have to change the modulus so that it is negative. Some people like doing that. I'm not one of them, but you can. The other option is, when you're dealing with tan inverse, to get to the other angle, all you have to do is add 180 degrees to it. So if I add 180 degrees to this, I get 213.7. So I'm going to use theta to be approximately 213.7 degrees. All right, so the polar form of this complex number would be z is equal to the modulus times cosine of 213.7 degrees plus I sine of 213.7 degrees. In parentheses. Now, one thing I neglected to mention is earlier I had the r next to both of the sine and the cosine. This form, it's just factored out. It's the same for both of them. So I just put it out front. So this would be the polar form of a complex number, negative 3 minus 2i.